Hello everyone. So in this video I'm going to summarize all that you have learned in the two previous very fleshed out videos, the one of fundamentals of vectors and the one on equations of lines and planes. Okay, so this is part of 1.1 vectors in 3 dimensions, equations of lines and planes. So let's get started. So I have here a version of the notes that you have on Kits, but this is a blank version so that I can write on it, and that way I can explain as I write. Yeah, that's how it will work. So first thing that we learned is about dot product and the cross product of two vectors. Yeah, so let's refresh what this means. So the dot products between two vectors A and B, this is a number, so the result is a number, the result is a scalar, which is given by the norm of A times the norm of B times the cosine of the angle between A and B. Now, when I say norm, and I use this notation of some vector V, so this is the norm of V, and this is another way of saying the length of the vector, yeah? And normally, if V equals a vector, let's say Vx, Vy, Vz, then the length of V is calculated using Pythagorean theorem as norm of V equals the square root of Vx squared plus Vy squared plus Vz squared, all square rooted, yeah? Okay, so that's the number, the dot product. But you know there's another way to calculate it, which is multiplying the components, the first component of A times the first component of B, plus the second component of A times the second component of B, plus the third component of A times the third component of B. And this is the dot product. And if you notice, you know that if you do the dot product of a vector with itself, the result is the length of that vector squared. Yeah, because you get Vx squared plus Vy squared plus Vz squared. Yeah. Okay, next, the cross product. So just remember that the cross product gets two vectors, A cross B, and the result is a vector, okay? However, what we can say is, so a way to calculate this vector is to use this determinant, and don't worry, we will learn a lot about determinants later, but we just write x hat, y hat, and z hat, the unit vectors, then we write the three components of A and the three components of B. And we calculate this determinant, and the result is a vector. But remember, the length of this vector, of this result, so the length of the cross product of A cross B, is equal to the length of A times the length of B times the sine of the angle between them. Yeah, remember that. Because the length of the vector is equal to the area of the parallelogram created by vectors A and B. So if this is a parallelogram, this area here gives us the length of the cross product. Okay, now quickly, just one very useful note. Imagine that you have a vector V over here. And now imagine that I define a unit vector U in some direction, arbitrary direction. And this is a unit vector. So when it is a unit vector, I use a hat on top of the U instead of the arrow. And this means that the length of U is equal to 1. Yeah? But now, if you imagine two axes, one is parallel to U and the other is perpendicular to U, yeah? Then the projection of V into these two axes can be very quickly found out by doing the dot product. For example, if we do the dot product of V times U, we get this length. So this length is the dot product of vector V dot the unit vector U, right? Because, why is that? Because here, if we look at the equation for the dot product, v dot u unit vector will be the modulus of v times the modulus of u, which is 1 because it's a unit vector, times the cosine of the angle between them. So it will be equal to the modulus of v times the cosine of the angle between them. And the angle between them is this angle here. So that's v cosine this angle, which gives you the projection of v onto this axis. So this is very useful, and you really need to have this inside you. So you don't need to really even have to think about this. This have to be inherent, second nature. So if you do v dot a unit vector, you are projecting the vector into that unit vector, into the direction of the unit vector. Okay, now what about the projection on the opposite axis? How can you find this length? Well, the length would be norm of v times the sine of the angle between them, right? So yeah, one way to do it is just to calculate the norm of the cross product between v and u unit vector, for a similar reason than we did with the dot product. So now the norm of this is the norm of v times the norm of u times the sine of the angle. And since the norm of u is 1, you just get norm of v times the sine of the angle. So this is a fast way of projecting a vector into directions using the dot and the cross product. And it's very useful to just remember it. So practice so many problems that this is just obvious eventually. Okay. Next, you studied a whole table of equations for lines and planes. But before I go into revising the table, let me point out something that often students don't really understand. And it's when we are using these equations, we always talk about this vector r that is involved in the equations, right? And this vector r is nothing else than a vector containing the coordinates x, y, z. And these coordinates x, y, z are simply, if we draw our coordinate axis, then we have a vector r, and we have the x, y, and z coordinates of this vector r. And this vector r is pointing to whatever entity we are describing. For example, if we are describing a line, yeah, then every point of this line corresponds to a certain value of x, y, and z, and that corresponds to a certain vector r. Yeah, so these are different vectors r. So there are infinitely different vectors r, and that's why r can be written as a vector that depends on a parameter lambda, which is like our slider, if you remember from the videos. So by changing this parameter lambda, we are changing the vector r so that we are moving throughout the line. Yeah. So it's very, very important to remember that this vector r is just x, y, z. So x, y, z will also depend on lambda, right? So once you fix lambda, you have a value for x, a value for y, and a value for z. So you could say that x is a function of lambda, y is a function of lambda, and z is a function of lambda. Yeah. So for example, we could have that when lambda equals 0, you have that vector r, but when you increase lambda to lambda equals 1, you are moving along the line. Yeah. And when lambda equals 2, you would be here. But this means that vector r has these three components, x, y, z, when a lambda gets a certain value. Okay. Another important thing to remember is that when you have two vectors, a and b, then the vector b minus a is equal to this vector here that points from the endpoint of a to the endpoint of b. That's the vector b minus a. Okay, remember, always remember that. So with these basic concepts, what we did is we built a table showing different ways of writing a line or a plane in different methods. I'm not going to go over this again because you already had a very long video about this, but I'm just going to fill this out very quickly, and I'm going to fast forward myself. So these were the equations that you learned about. Different ways of writing a line and a plane in parametric form, or using products, or in component equations, right? But what I noticed that some of you don't understand is that you can actually get the parametric form. For example, r of lambda equals r0 plus lambda v. That's the parametric form of the line, right? So actually what these vectors are, you can actually write vector r as x of lambda, y of lambda, z of lambda. Then vector r0, which as you know is any point pointing towards the line, you can write it as its coordinates, x0, y0, z0. And then vector v, which is any vector that is parallel to the line, you can also write it in terms of its coordinate, vx, vy, and vz. Yeah. So you could write this equation as x of lambda, y of lambda, z of lambda equals x0, y0, z0 plus lambda vx, vy, vz. Which, if you think about it, is nothing else than three different equations, right? So this would be the equation x of lambda equals x0 plus lambda vx, then y of lambda equals y0 plus lambda vy, and z of lambda equals z0 plus lambda vz. So the parametric form is just a way of saying three equations at the same time. Yeah. Okay. Next, we move on to the equation of a sphere, which is the following: r of the sphere minus a vector c, which is the center of the sphere. Yeah, it's a vector pointing from the origin to the center of this sphere, equals the radius. Let's call it capital R. That's the radius of the circle or of the sphere. So that's the equation for a sphere. And finally, you also saw a table on different equations for calculating distances between lines and planes and between planes. Yeah. So let me again fill it up very quickly in fast forward mode. Okay, so these are the equations. The usual questions that students ask me after they watch the video is that they don't really understand what this r line means or this r plane means. So what this means is you can find any point whatsoever that lies on the line. So r line means any point on the line. Okay, so for example, say that your line is r line equals r0 plus lambda v. So any value of lambda would work, yeah, because every point in the line is given by any value of lambda. So for example, the easiest one would be to say, okay, lambda equals 0, for example. So then you could use r0, for example, yeah. So any point that you can find would work in this equation. For the second equation, distance between a point and a plane, so any vector pointing to any location on the plane would work, yeah. So that would be r plane. And then finally, the distance from line to line, you need to find any point on the first line minus any point on the second line. Again, any point will work. So you just have to find one. Okay, and one more thing. So you will notice that here I have used the norm of a vector using two lines, but I have used here only one line. Why is that? Because when I use two lines, I mean the norm of vector. But when I use only one line, it's because what is inside is a scalar, and this means the modulus or the complex amplitude of a scalar. So in order to distinguish these two operations, I use the double lines for vectors, so you calculate the length of the vector using the double line, or the single line to calculate the modulus. For example, modulus of -1 is 1, modulus of -3 is 3. Modulus of 1 plus I is the square root of 2, which would be the complex modulus of this number. Yeah? So for that I use a single line. So the difference will always be that the double lines has a vector inside, while the single line has a scalar. That's why in the equation for the distance between the point and the plane, we have a single line, because what is inside is a dot product. So the result of the dot product is a scalar, yeah? So this thing will be a scalar. That's why I calculate the modulus of that scalar, okay? And now finally we can review the properties of dot and cross products. And these are actually very, very useful. So, first important property, the dot and the cross product are linear operators. And what does this mean? This means that if you apply, for example, the dot product to a linear combination of vectors, so remember, linear combinations means alpha A plus beta B. So it's a scalar times one vector plus a different scalar times a different vector. That's a linear combination of two vectors, yeah? If you do the dot product of that with some other vector, the result is the linear combination of the dot products with the other vector, yeah? So you can literally get alpha outside and do alpha times the dot product A times C plus beta times the dot product B dot C. And this would be also true if instead of dot we have the cross product. Okay, so this is the linearity of the dot product and the linearity of the cross products. Two very important properties. You will hear more about them in the following chapters. Next is that the dot product is symmetric. What does this mean? It means that A dot B is equal to B dot A. Okay. And finally, another interesting property is that the cross product is antisymmetric. Actually, antisymmetric is written with I, not with Y. Antisymmetric. Okay. And this means that A cross B equals minus B cross A. So if you swap the order, you have to change the sign of the result. And that's all for now. So next, you can do some problems.